When you want to study some phenomenon, you collect data. And of course, the more data you collect, the better you understand the phenomenon. It's just common sense. And there's a name for this common sense in probability. It's the weak law of large numbers. So the weak law of large numbers says that, say we perform n identical and independent trials say of some experiment. Let's let xi be the outcome of the ith trial. And let's let the expected value of xi be mu for all I. The variance of xi be sigma squared. Then for all numbers epsilon greater than 0, the average outcome so we sum the first n outcomes divided by n satisfies the limit as n goes to infinity of the probability that the average differs from the expected value by more than epsilon is 0. So let me write these words in English again. So as n goes to infinity, the probability that the average and the expected value differ by more than epsilon goes to 0. Alright, so this actually isn't very hard to prove. Let me erase the statement of the beginning of the statement of the theorem here to have some room to prove it. Let me summarize it very briefly. So the expected value of xi is mu, variance of xi is sigma squared for all I, and we're performing n trials. So to prove this, let's let y be this sample average. N observations, add them up, divide by n. And the expected value of y is the expected value of x1 over n plus x2 over n, etc., up to xn over n. Expected value is linear, so this is 1 over n. Expected value of x1 summed up to 1 over n expected value of xn, which is, these are all the same, 1 over n mu added together n times, so that's just mu. So that means that the probability we have here is the difference between y and its expected value. All right, now by Chebyshev's inequality, this is less than or equal to the variance of y all over this number squared. So we need to find the variance of y. All right, let's do that in the space that we used for the expected value of y. So the variance of y is, write out what y is. It's the variance of x1 over n plus x2 over n, etc. Now since these are independent, we can take the variances separately. I'm going to need a couple more steps. Normally we would need to add covariances here, but since x1 through xn are assumed to be independent, we just need to take the variances of these separately. No covariances. When we take variance of a constant times something, we can pull the constant out, but it becomes squared when we pull it out. So this is 1 over n squared variance of x1 summed up to 1 over n squared variance of xn. These variances are all the same. They're all sigma squared. So we're adding up 1 over n squared sigma squared n times. So I guess we get sigma squared over n. So by Chebyshev's inequality, the variance of y over epsilon squared is going to be sigma squared over n epsilon squared. And again, the probability that y differs from its expected value by more than epsilon has to be less than or equal to this. Now this fraction is number over n times number. These are constants, so as n goes to infinity, sigma squared over n epsilon squared is 0. Because n is the only thing that's going to infinity. These are constants. So this means that if we roll a pair of dice many times. And take the average of rolls so far each time. So we update the average after each roll. Then for any number epsilon greater than 0, the probability that our average is not in the range 7 minus epsilon, 7 plus epsilon. Now 7 is the expected roll, because we're rolling 2 dice. Each one of them has an expected roll of 3.5, so 2 of them is 7. So the probability that our average is not in the range 7 minus epsilon, 7 plus epsilon gets lower as n gets larger. The end.